All right, so we're going to take a look at solving and graphing linear inequalities. So just kind of a review. If I use one of these symbols, so like less than equal to, greater than, those inequality symbols, instead of an equal sign, that is defining that my value of x, so when we talk about solutions and solving, instead of x having only one possible value that can make it true, it's going to be a whole range of values because like here we're looking for 3 times something minus 12 to be anything as long as it's less than 3. So there are a lot of numbers that would make that true, but we're going to narrow it down to specifically like which range of numbers. So that's the idea behind inequalities, is we're looking at a range of solutions, not just single solutions. So when we go to do the algebra to decide, well, what numbers do work for x, again, we could probably guess and check a bunch of numbers that work, but to define like the full range, we are going to be applying our same solving steps that we use for equal signs. So I'll put in parentheses an equal sign. So if we pretend that it's an equal sign there, we are still, like we can draw our line and do all of our same solving steps to get x alone. So x is on this side, so I would have to add 12 to both sides. And then this symbol right here, so it's not actually an equal sign, but we're just applying those same steps. This sign here carries straight down, so it's still a less than symbol. And then 3 plus 12 is 15. And then my next step would be to divide both sides by 3. And that would leave me with x. And then again, bring down that symbol is still less than. 15 divided by 3 is 5. So this is telling us that any number that is less than 5 would be a solution to this inequality. So I could plug 4, 3, 2, 1 decimals. So the not equals to just means I can't plug in the number 5. That would not be false. That would be false because I don't have the or equal to. And then our last step to create a visual for this is to graph it. So we graph one variable inequalities on a number line. So we're just going to sketch a little number line here. I don't have a ton of room. So if I sketch a number line, and then I'm just going to mark a few numbers. So I'll do 5 because that's kind of the boundary of my inequality. And then to the right of 5 would be 6. And then 4, just to get a sense of where we are on the number line. And then I am going to use that one. Follow then these rules. So if I have the underline underneath that symbol, that means it's also including. So including the boundary value. So like in that first example, 5 was the boundary value. And then if I don't have the underline like over here, this is not including that value. So the boundary. So to represent on a number line whether we're including or not, we would either mark that boundary value with an open circle or a closed circle. So because this is not including that boundary of 5, I would use an open circle. So I'd make an open circle around the value 5. And then this symbol here is telling me that I could plug in any number less than 5 and it would make this true. And if you're kind of confused or don't remember which way the symbol is that less than, greater than, you can put numbers on either side in. So if I checked 4 less than 5, or put 6 in for x, 6 less than 5. So this one here would be true, this would be false. So that means that any number less than 5 is going to be a solution to this. So like I could plug in 4, 3, 2, 1, anything down here, but anything 5 and above would not make this true. All right. then if you would like to just try the rest on your own and go check the completed notes on Google Classroom, that might be a way that you want to work through this. Otherwise, this will be a long video. I will show the rest of the examples. And if you want to just come back and jump to the one that you might be stuck on, that would be my recommendation for working through the rest of this first part of notes. So this first video, I'm going to stop right here and then make a second video for that bottom part. All right, so for B, again, we draw our line, apply regular solving steps. So I would distribute that 5. So 6 plus 5 times 2 is 10 minus 5x, and then carry that symbol down, 41, and then we have 16 minus 5x. 5x is less than 41. Subtract 16 from both sides. And then we have negative 5x is less than or equal to 25. And then I'm going to highlight this rule right here. So there is like a little exploration we can work through to help us understand why this is a rule. But whenever we're working with inequalities, if we end up having our solving step to both sides be multiplying or dividing by a negative number, then that symbol needs to reverse. All right, so multiplying or dividing. So basically you're taking like the number line, and if you multiply or divide a bunch of positive numbers by a negative, it's going to reverse your number line. So we have to flip that symbol. So I'm dividing by negative 5. So I'm going to star that. So that means that I'm going to apply this little rule here, and I'm going to reverse this symbol the other direction. So then when those cancel, x is now greater than or equal to positive 25 divided by negative 5 is a negative 5. All right, and then when I go to graph that, I'm gonna run out of room here. So if I put negative 5 in the middle, so looking at a number line to the right of negative 5, we're going towards 0, so this is negative 4, and then to the left is negative 6. Remember, the negative numbers go the opposite direction of the positive numbers. And then since this isn't or equal to, we're going to make a closed point there. And then any value that is greater than negative 5, so greater than is going to the right, would be a solution. And just like any other problem, we can plug in like negative 4, negative 3, negative 2, any number this direction back in for x, and then simplify each side and verify that that symbol is true between those two values. Put that on there for now. And then for C, if I draw my line, so remember we want to get rid of the add subtract before, like the multiply divide. So this is a positive 7, so we're going to subtract 7 from both sides. So I want to point out, because it's a common mistake, so subtraction, that's a negative, but it's not multiplying or dividing, so we're not going to use this rule here. So let's go away. And then remember, it's a negative 3/2 x. So carry that negative down, and then negative 5 and negative 7 is negative 12. And then to get rid of this negative 3/2, so I can either do 2 steps, multiply by the 2 to cancel that, and then divide by 3, or just to save room, I can multiply by the flip of that fraction. So if I multiply by 2/3, that will end up canceling both like the 2 and the 3. But then notice that we're multiplying by a negative, so this rule is going to apply. And multiply this side also by negative 2/3, so I have to keep it the same. And then, so because I multiplied by negative, I have to flip that symbol the other direction. And so on this side, because they canceled, I'm just left with x. And then on this side over here, so to multiply fractions, we need to like multiply numerators, multiply denominators. So I can make any number of fraction by putting over 1 and then go straight across top and bottom. So on the top we have negative 12 times negative 2, so that's positive 24. And then the bottom 1 times 3 is 3. And then I can simplify that 24 over 3 to 8. So x is going to be less than or equal to 8. So any number, if I draw my number line here, so 8, and then we're in positive, so that would be 9, that would be 7. And since it's a or equal to, we have that underline, it's going to be closed, so I'm including the boundary value of 8, and then any number less than 8. So 7, 6, 5, 4, 3, 2 into the negatives. All of those values, this direction, if I plugged them back in, they should make this a true statement. That side should be larger than that side. All right, and then this example here, so we're really gonna run out of room. I'm just gonna call that. So if so something a little bit different is gonna happen here. So when I distribute that, we have colors. So we carry down the greater than, and then we have 2x minus 10 against 2x minus 3. So you might be able to kind of see already, like 2x and 2x are the same here and here. Subtracting 3 and subtracting 10 are not going to give the same result. But if we go through their solving steps and I were to subtract 2x, those would both cross off, and I would just be left with negative 3 is greater than negative 10. So I've lost my x, and I just have an inequality statement. So what I want to do is evaluate. If I look at a number line, so there's 0. So negative 3 would be like right here, and then negative 10 would be farther to the left. So is negative 3 greater than negative 10? Is that a true statement? Yes, it is true. Negative 3 is further to the right. So if this is a true statement, what that means is that no matter what value I plug in for x on either of these sides, they're always going to cancel each other out, and I'll always be left with the true statement. So I can put any number I want for x, and it's going to be a solution. So what we would say here is we have infinite solutions. Or we might see it written as, like mathematically, it's all real numbers. So you might see it written either way, but it just means any number, positive, negative, decimals, zeros, fractions, they all make it true. All right, and then that right there for now. This next example, so again, something different is going to happen from the top row and different from this example. So if I distribute that 7, we'll have 7x minus 28 against 7x plus 6. So when I subtract those 7x's, I get 6 is less than negative 28. So this is saying that a positive 6 is going to be smaller than a negative 28. That is a false statement. So what that means is that there will never be a value of x that I can plug in to make this equation true. Okay, it's always going to be false. So we would say that there is no solutions. Okay, no values of x will make this, will satisfy this inequality. And then this one here, is it going to end up being the same actually as this first one? So just real quick, I'll have 2x is less than 2x plus 2, and then bring that 3 down. So my 2x's, when I subtract them, minus 2x, they will cancel, and then I'll have 0 is less than 5. 0 is less than 5, that's true. So that would be like the all real numbers or infinite solutions. All right. So I'm actually going to stop the video here because it's a little long, and then I will post a part 2 to do the applications and the compound.